Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum, dear students. Hope you will be in good health. This is lecture 13 of the numerical solutions of partial differential equations. We have started parabolic partial differential equations and discussed three schemes, namely explicit scheme, implicit scheme, and Crank-Nicolson scheme. Also, we have tested all these three schemes with the help of different examples. In today's topic, I will discuss about local truncation error and stability of the explicit scheme. The following are the contents of today's lecture. First, we will discuss about the local truncation error. Then, we will discuss the stability of the explicit scheme with the help of matrix method. And finally, I will end with references. Prior knowledge. Let me recall the basic equation, which is heat equation, ut minus uxx is equal to 0, where ut represents partial derivative of u with respect to t and uxx represents twice partial derivative with respect to x. This equation is parabolic in nature. Forward difference scheme for ut, which is approximately equal to uij plus 1 minus uij divided by k plus order of k, where this order of k represent the rest of the series having higher powers of k and k power 1. Central difference for uxx, this is approximately equal to ui minus 1j minus 2 uij plus ui plus 1j divided by h square plus order of h square. Remember, we have studied in detail about the derivation of this forward difference scheme and central difference scheme, and also about the nature of this equation. Substituting equation 2 and 3 in equation 1, we are getting the difference equation which is given in 4. Fij of u, this is a notation for this difference equation. Remember, we have two equations mainly. One is the partial differential equation which is given in 1, and the other is difference equation which is given in 4, and this difference equation is the approximation of this equation. Definition of the local truncation error. For local truncation error, let Fij of u is equal to 0 represents the difference equation approximating the partial differential equation at the mesh point ihjk with exact solution u. Remember, this small u is the exact solution of the difference equation, and the mesh point ihjk, this can also be represented as just ij or xi and tj. If u is replaced by capital U at the mesh point of the difference equation, where capital U is the exact solution of the partial differential equation, then the value Fij of u is called the local truncation error, which is denoted by Tij at the mesh point ihjk. Remember, this Fij of u clearly measures the amount by which the exact solution values of the partial differential equation at the mesh point do not satisfy the difference equation at the mesh point ihjk. And this is the definition of the local truncation error. Now we consider an example to show that how one can compute the order of the local truncation error. So in this example, we consider the heat equation and calculate the order of the local truncation error of the explicit difference approximation to partial u by partial t minus partial square u or partial x square is equal to 0 at the mesh point. The solution is, consider the difference equation for the partial differential equation, which is Fij of u is equal to uij plus 1 minus uij divided by k minus ui minus 1j minus 2 uij plus ui plus 1j divided by h square is equal to 0. From difference equation we can write Tij is equal to Fij of u is equal to uij plus 1 minus uij divided by k minus ui minus 1j minus 2 uij plus ui plus 1j divided by h square. In previous slide we discussed about the local truncation error, that when we replace capital U, which is the solution of partial differential equation, and the difference equation, we are getting the local truncation error. So this is the local truncation error Tij. Now you saw in previous slide that we have ui plus 1j, ui minus 1j, and uij plus 1. So by using Taylor series expansion, we can write ui plus 1 comma j is equal to ui plus 1 h comma j k, and ui xi uxi plus h comma tj. Remember, all these threes are the same, and different kind of notation has been used. You can use this kind of notation, you can use this kind of notation, and you can also use this kind of notation. All these three notation means that we are interested in the value of u at the point xi plus h comma tj. Now using Taylor series for this uxi plus h comma tj, this will be equal to uij plus h partial u by partial xij plus 1 by 2 h square partial square u over partial x square at the point ij plus 1 by 6 h cube partial cube u over partial x cube at ij plus and so on. Since we are using the Taylor series corresponding to this xi plus h, so that's why we are using the step size h. Similarly, the Taylor series for ui minus 1j is equal to uij minus h partial u by partial x ij. Here is the sign negative, so this negative sign is due to this sign, plus 1 by 2 h square partial u square u over partial x square ij minus 1 by 1 by 6 h cube partial cube u over partial x cube at the point ij plus and so on. And similarly, the Taylor series expansion for uij plus 1 is equal to uij plus k partial u by partial tij. Here we have used k because we are using the Taylor series for xi tj plus k. So in the about two cases, in ui plus 1j and ui minus 1j, we have used h because we have used Taylor series for xi uxi plus h and xi minus h, and here we are using for tj plus k, so that's why we are using k over here. And plus 1 by 2 k square partial square u or partial t square at the point ij and so on. Now using ui plus 1j, ui minus 1j, and uij plus 1 in the truncation error, which is basically equation 5, we have Tij is equal to partial u by partial t minus partial square u or partial x square at the point ij plus 1 by 2k partial square u or partial t square ij and so on. Remember, this equation has been obtained from that local truncation error by plugging all these three values and rearranging the terms. Now u is the solution of the differential equation, so that will satisfy the differential equation at the mesh point. So partial u by partial t minus partial square u or partial x square at the point ij, that should be equals to what? 0. So by plugging this part is equal to 0 in this equation, we are getting Tij is equal to 1 by 2k partial square u or partial t square minus 1 by 12 h square partial 4u or partial x4 at the point ij and so on. Remember, to find out the order of the local truncation error, we consider the principal part of the series, and principal part of the series containing those terms having least power of k and least power of h. So you can see over here that the least power of k in this series is just k power 1, and the least power of h is 2. So we represent rest of the expressions, whether k power 2, k power 3 and so on, just we write order of k, and for h square, h power 4 and so on, for this just we write order of h square. Therefore the Tij will be equal to order of k plus order of h square, and this expression can also be written as order of k plus h square. So this means that the order of the local truncation error is order of k plus h square, where order of k and order of h square, this basically represents all the term having power of k starting from 1 and so on, and similarly in order of h square, this containing all the terms having least power of h is 2, and so on, h power 4, h power 6 and so on. So Tij is order of k plus h square. So this means that the order is order of k plus h square, and this requires that the value of k should be smaller than h, and this can be observed from the stability conditions then, because there is a relation between the alpha k and h square, which we have discussed in previous lectures. So in the explicit scheme, the order is order of k plus h square. Now we are moving toward the stability of the explicit scheme by matrix method. So as you saw in the previous lecture, in the previous slide, that the truncation error in the explicit scheme is order of k plus h square, and the scheme works in some cases, while in some cases this gives drastic results. To explain the difficulty that in some cases the scheme works but in some cases this gives drastic results, we need to look at the stability of the explicit method. Now to start the stability, since the initial condition is defined by u at xi0 is equal to f of xi for the parabolic partial differential equation, because there is one time derivative and twice space derivative, so there should be two boundary conditions and one initial condition, and that initial conditions at discrete values are given by uxi 0 is equal to f of xi, where I starting from 1 reaches up to m minus 1, where m represents the number of points along x-axis. Suppose that an error E0 is equal to E10, E20 and up to em minus 10 whole transpose is made in the corresponding initial data. U0 is equal to f of x1, f of x2 up to f of xm minus 1 transpose. This means that we are considering the internal points only, because at the boundaries the error is 0. So corresponding to this component, let's say we have an error, this one, corresponding to f of x2, let's say we have an error E20, and corresponding to f of xm minus 1, let's say an error em minus 10 exists. This is also applicable for any particular step. The choice of initial step is simply for convenience. Since the matrix of form of the explicit scheme is given by uj plus 1 is equal to uj, and we did this scheme in case of explicit scheme and also applied this to some test problems. So you saw in previous lectures that this uj plus 1 is equal to auj. This is the matrix form of the explicit scheme. Now for j is equal to 0, we have u1 is equal to u0. We can obtain this equation from this equation by plugging j is equal to 0. Therefore an error e0 will propagate to u1. How? Because u1 will be equal to u0 plus e0, and this u0 is the initial data and this is the error corresponding to this initial data. So that's why this u1 will be equal to au0 plus ae0. So this ae0 is the approximation of this u1, and this ae0 is the error which propagate in u1. And similarly and for j is equal to 1, u2 will be equal to a u1. So a square e0 error that will propagate in the next step, and this process continues at the nth time step. The error and un due to e0 will be an e0, because when we substitute u2 is equal to au1, and instead of au1 when we substitute this value, so we are getting u2 is equal to a square u0, and plus that will be a square e0. So this means that an error a n e0 will propagate at the nth time step due to this error e0, which we consider in the initial data. Now the method will be stable when these errors, that means that the error which propagate to u1 a e0, which propagate to u2 a square e0, and so on. The method will be stable when all these errors do not grow as n increases. But this is true if and only if for any initial vector we have this the norm of this vector is less than or equal to this vector. Because when we say that this error a e0 is not greater than e0, then the norm of this vector should be less than e0. And similarly, when we say that this error an e0 is not greater than e0, then this will be true only if and only if the norm of this vector is less than or equal to e0. Because if the norm of this vector is greater than 0, then this means that the propagation of error increases. But in the definition of stability, the method will be stable when these errors do not grow as n increases. So that's why this is true if and only if the norm of this vector will be less than or equal to e0, and e0 vector has been defined previously. Hence we must have the norm of an will be less than or equal to 1, because when an e0 norm less than or equal to e0, then we must have the norm of this an will be less than or equal to 1, because in norm we have an e0 will be less than or equal to an norm into e0 norm. So when this an norm is greater than 1, then an e norm will be not less than e0. So that's why an norm will be less than or equal to 1, then an e0 norm will be less than or equal to e0. And this is a condition. For this we use a theorem on page 446 in the book of Burden and Fair, that when this norm less than or equal to 1, then the spectral radius of this an that should be less than or equal to 1. So spectral radius of an that will be equal to spectral radius of a whole raised to the power n less than or equal to 1. Now this explicit scheme is therefore be stable only if the spectral radius of a less than or equal to 1, because when this spectral radius of a whole raised to the power n less than or equal to 1, if this value itself less than 1, then the power of that less than 1 value will be less than 1. So that's why the explicit scheme is therefore be stable only if the spectral radius of a will be less than or equal to 1, where the spectral radius of a represents the maximum eigenvalue of the matrix A. Since A is tridiagonal matrix, you saw in previous lectures that an explicit scheme, when we converted the scheme to matrix form, so on left hand side we have uj plus 1, on the right hand side we have the coefficient matrix A and uj, and that A was a tridiagonal matrix of dimension m minus 1 cross m minus 1 when boundaries are not included. And here we use a results that the eigenvalues of the tridiagonal matrix are mu I is equal to 1 minus 4 lambda sine I pi divided by 2m all raised to the power square. You can see this results from the book of linear algebra, where I starting from 1 reaches up to m minus 1. So the condition for stability consequently reduces to that mu I mod will be less than or equal to 1, because the spectral radius of that matrix A should be less than or equal to 1, and the spectral radius basically represents maximum eigenvalue. So this mu I is these are the eigenvalues of a matrix, and absolute value of this should be less than or equal to 1. This means that the spectral radius is less than 1. So that's why we say that the condition for stability consequently reduces to mu I mod will be less than or equal to 1, and mu I mod is basically equal to mod of 1 minus 4 lambda sine square I pi by 2 m whole raised to the power 2. Now we use an inequality that if x mod is less than or equal to 1, so we can also write this inequality as minus 1 less than or equal to x less than or equal to 1. So this condition or this statement can also be written as minus 1 less than or equal to 1 minus 4 lambda sine I pi by 2 m whole raised to the power 2 less than or equal to 1. So here we are using this term, this whole term, instead of x. So that's why we can write this inequality as. Now subtracting this minus 1 in whole inequality, so this implies that minus 2 will be less than or equal to minus 4 lambda into sine I pi by 2 m whole raised to the power 2 less than or equals to 0. Or we can also write the previous statement as that multiplying this inequality with minus sign, so order should be reverses. So this implies that 2 will be greater than or equal to 4 lambda sine I pi by 2 m whole raised to the power 2 greater than or equals to 0. Now you can see that this part of the inequality is obvious, because if the value of sine is 0, then that should be equals to what, 0, and this inequality holds, and for rest of the values that should be greater than 0. So this part is obvious. From this part, 2 greater than or equal to 4 lambda sine I pi by 2 m whole raised to the power 2, we can write that this will be less than or equal to 2, and this implies that 4 lambda, since this is true for all values of sine, so the maximum value of sine is 1. So that's why this implies that 4 lambda will be less than or equal to 2, and less than, or this implies that lambda will be less than or equal to 1 by 2, where lambda is basically equal to alpha square h square divided by k. This mesh ratio already we defined in explicit scheme. Hence the scheme will be stable if this lambda is less than or equal to 1 by 2. So we have to adjust this lambda accordingly. If the value of lambda is greater than 1 by 2, in case of explicit scheme, this will give you drastic results. This is the stability condition, that this lambda will be less than or equal to 1 by 2. So according to this, we have to adjust our h and k. Homework: discuss the stability of implicit scheme with the matrix method. As we discussed the stability of explicit method, discussed as the stability of implicit method with the help of matrix method. These are the references. Students have the book of R.L. Burden and Fair in soft as well as in hard form. Also the book of G.D. Smith in hard and soft form. So for local truncation error, you can see the topic from this book, and similarly for the matrix method for the stability, you can see the method, the book of Burden and Fair as well as the book of G.D. Smith. And if you have any problem in today's lecture or in the homework, you can contact me through email. Thank you very much.